questions from GATE 2022, focusing on engineering mechanics and theory of machine subjects. In this paper, there were total 4 questions asked for 1 mark from these 2 subjects, and there were 5 questions for 2 marks were asked from these 2 subjects. So in total, there are 14 marks questions were asked. So let's solve them one by one. Coming towards the first question. A massive uniform rigid circular disc is mounted on a frictionless bearing at the end E, as shown in this figure here, of a massive uniform rigid shaft AE, which is suspended horizontally in a uniform gravitational field by 2 identical light inextensible strings AB and CD. So basically we have AB and CD two strings and a uniform rigid shaft, and at one end of the shaft we have attached the rigid circular disc. G is the center of mass of the disc, and overall basically shaft and disc assembly. Small g is the acceleration due to gravity. The disc is then given a rapid spin omega about its axis in the positive x direction. So basically we can clearly see here, if you look from this end, it will be a clockwise, and if you look from this end, it will be a counterclockwise. The direction of rotation is defined by using right hand thumb rule. If string AB is suddenly cut, so they are cutting the string AB at a certain point, assuming negligible energy dissipation, the shaft AE will. What will happen to shaft AE? Let's try to understand. So this is from the gyroscopic effect, or the gyroscope topic from theory of machines, and these are the options they have given, like rotate slowly, all the options, but the distinguish is here whether it's a negative z direction, positive z direction, about positive y direction or negative y direction. Let's try to understand the situation here. Whenever we are, let's say, understanding a gyroscopic effect, we draw the diagram. So in this case, I would say AE is one of, let's say, the vector here. And then what we are doing is we are breaking this AB at a certain point. So the shaft will look something like this, basically. Maybe something like this we will have. This is how it will look like, because now you have only one string attached to the shaft, that is CD. The other one, AB, we are cutting it. So indirectly, we are, let's say, rotating it by in some angle. Okay, we are rotating it by some angle. We don't know, let's say theta, and new point OE will change to, let's say, OE dash. So this is new direction of our angular velocity vector. So as they have mentioned, the angular velocity vector is directed by using right hand thumb rule. So if let's say the direction of angular velocity is this, then you can say by right hand thumb rule it is like this. Okay, and now, so basically we are, by cutting the string, the active gyroscopic torque is in this direction. However, there will be a reactive gyroscopic couple which will counterbalance it, that will be in the opposite direction to the active gyroscopic torque. So you can say that this E dash E, this particular torque, I'll draw it in a red color, is, we call it as a gyroscopic effect or a reactive gyroscopic torque. And if you apply your right hand thumb rule on it, because yeah, that's how we define the direction, it is something like this, right? It is something like this, and this is going down, the arrow is going towards down. So looking, yeah, basically it is in counterclockwise direction and our thumb direction is pointing towards downside. And if you look into the options, we can clearly say that positive z direction is the upward and the negative z direction is the downward. So in this case, the correct answer would be option A, that uh, if you cut the string AB, suddenly cut the AB, string, then the shaft AE will basically rotate about negative z direction because of this gyroscopic couple. Okay, um, so that's the answer in this case. Option A is correct. Coming towards the next question. This one is from the mechanics. We have a square plate supported in 4 different ways. Configurations P to S as shown in this figure. And we have also a couple in all the figures. The couple C is applied on the plate. Assume that all members to be rigid and massless and all joints to be frictionless. All support links of plates are identical. Question is like the square plate can remain in equilibrium in its initial state for which one or more of the following support configurations. So here we have to tell in which configuration out of these 4, or in which situation out of these 4 situation we have uh, the equilibrium. We know when we say the system is in equilibrium, if sum of all the forces and moments is equal to 0, we say that system is in equilibrium. In this case, we are the, let's say in this case, the only thing which is external is the couple or the moment, you can say. The C is the couple they are using here. So we have to check whether we are balancing that couple in these all 4 situations or not. If we are balancing in these all 4 situations, then of course we will say that the system is in equilibrium. If we are not balancing it, then we can say that system is not in equilibrium. So let's try to understand all these 4 configurations one by one. Okay, I'll use maybe uh, the some other uh, pen here. Let's take it a green pen just to distinguish the active couple in this case and the reaction couple, because we have um, supports in a different way. If you start with the first, how the reactions will look like. Reactions will be like this, or maybe like this. Okay, direction may change. Okay, whatever direction I am giving here may change. Maybe it will be in opposite to that, but overall, your one force direction is in this direction, another force is in this direction, and one force is in the upward direction. Maybe it will be upward or downward. I don't know. Uh, Depending on when we calculate it, we will get. However, whether it's creating any couple, whether it's creating any moment about the CG, no, right? It's not creating any moment. So the first case is like the reactions are not creating any couple which will counterbalance the active couple, okay, or which is the couple C applied on this. So in this case, I would say this is not a equilibrium condition. In second case, if you see, uh, we have one reaction point. Let's say here we have one reaction at point here, we have one reaction at point here, and we have one reaction at point here. In general, you can see that there is a couple which is getting created. So when we have two opposite forces separated by a certain distance, okay, two equal and opposite forces separated by a certain distance, it forms a couple. In the same way, in this situation, it will form a couple, and both of them are in counterclockwise direction, whereas applied couple is in the clockwise direction. So we can say that this can be this is a situation of a equilibrium where the reaction forces or the reactions are forming a couple which will balance the couple acting on this plate, and hence we can say that yes, this is the situation of a equilibrium. uh, Going towards the third option here also, let's say the reaction is like this and reaction is like this, and basically the these two are again equal and opposite forces separated by certain distance forms a couple, and this is a counterclockwise couple which will balance the clockwise couple. Hence I will say that this is also a case of an equilibrium. And the last question. So in this case, imagine a situation like if we have one force in upward direction and one reaction in the downward direction. Okay, because of course the system will try to be in equilibrium when we have active couple. The reaction at, let's say, point here, let's say point A, will be in upward direction. Reaction at a point B will be in a downward direction in order to counterbalance this couple. Okay, so this is a counterclockwise couple which is getting generated here, um, and because of these reactions at the supports, and that will try to balance the active couple. Okay, and hence this will be also an example of an equilibrium. So the correct option in this case is option Q, okay, R, and S. Okay, so basically the B, C, and D options are correct because they are saying uh, the square plate can remain in equilibrium in its initial state for which one or more of the following support configurations. So this is like a multiple options type of question where you have to choose the multiple answers. Okay, in this case, you can say that the system will be in equilibrium in the situation Q, R, and S, and it will not be in equilibrium in case of P because the reactions in figure P are not creating a couple, and which will counterbalance the active couple. Okay, I hope it is clear. Coming towards the next question. This question is again from the mechanics. In this case, let's see what they're asking. A rope with the two masses, two massless platforms at its two ends over a fixed pulley as shown in the figure. So we have a pulley and then these are two platforms. There are, let's say, the narrow slots the disc is having and having equal weight of 20 Newton each can be placed on the platforms. The number of discs placed on the left side of the platform is N, and that on the other side of the platform is M. Okay, let's see. That is what they are saying. If it was found that for n is equal to 5, means if you put 5 discs on the left hand side, m is equal to 0. Okay, means you are not putting any disc on the right hand side. A force F is equal to 200 Newton. Okay, if you apply here F of 200 Newton without any plate, just apply the force of 200 Newton. You look at this figure number 1, is just sufficient to initiate the upward motion of left side platform. So if you apply a 200 Newton force here, let me write it here, the motion will just about to start in the upward direction. Okay, so that is a limiting case or equilibrium case, that if you just think the 200 Newton is in equilibrium case, you can say, or the limiting case for just moving the 5 discs kept on the left side of the platform. This is the given data. The question they are asking is, if the force F is removed and then the minimum number of M means the number of plates or disc kept on the right hand side required to prevent downward motion, because if you don't put this 200 Newton, this will come down, and we want to avoid it. So to do that, how many number of plates or how many number of discs you have to keep on the right hand side, so that they are asking us to find the value of M required to prevent downward motion of the left side platform. Okay, so they are giving us two situations. Let's try to understand the first situation which they have given. In the first situation, as we can clearly see, they have kept 5 plates on the left hand side. One plate is having 20 Newton weight. 5 plates, if they are keeping, means 100 Newton is applied on the left hand side, in simple words. Okay, so 100 Newton is applied on the left hand side, and if we apply 200 Newton on right hand side, that is a case of equilibrium. Why? Because of course, like, there are some friction factors are there. Okay, so this is our pulley. We know that at this point it will start moving in clockwise direction, and the left side will go upward. So the tight side is the right hand side, T1 divided by, let's say, T2. Okay, let me, okay, let's call this as maybe T1 is your 200. This is T2. T1 by T2 is equal to e to the power mu theta. Theta is a lap angle in this case. So T1 is 200, T2 is 100, is equal to e to the power mu into theta is pi in this case, which is in radian. Okay, so I will say mu pi is equal to ln of 2. So mu will be, that is the coefficient of friction, is 0.22 something you will get. Now we'll talk about the second situation on the next figure, on the next slide. We are still having 100 Newton force, but now we are removing the 200 Newton force, but applying or putting some m number of, let's say, the discs. So I'll say it as a T3. So T1, and we just have to find the condition or how many plates to be kept on the right hand side so as to avoid the motion of the left hand side in the downward direction. So it will rotate in the counterclockwise direction. So T1 will be 100. So I'll directly write here 100 divided by T3 is equal to e to the power mu pi again. So T3 can be e to the power mu pi is 2. Okay, we have already, or here you can say that to the power mu pi is 2, and that you can refer here. So T3 can be written as 50 Newton. Okay, because e to the power mu pi is 2 and T3 will be 50 Newton in this case. 50 Newton means how many plates? In one plate, you can say one plate belongs to 20 Newton. So number of plates in this case is 50 by 20, which will be 2.5 discs, more than 2 discs. So it means minimum number of discs will be 3. So that's why you have to keep minimum 3 discs to avoid the motion of the 100 Newton um, side, or to avoid the motion of the left hand side in the downward direction. So the correct option in this case is 3. Okay, we want to prevent the downward motion of the left hand side. Okay, so if you put 2 discs, it will of course go down. If you put 3 discs, it will not. Okay, that's why the answer is 3 in this case, because the calculation gives us 2.5, means more than 2 discs are required. So the 3 is the correct answer in this case. Coming towards the next question. This is from the vibrations. For a dynamical system governed by an equation, the damping ratio is zeta, that is equal to 1 upon 2 pi ln of 2. The displacement x of this system is measured during a hammer test. A displacement peak in the positive displacement direction is measured to be 4 millimeter. Neglecting higher powers greater than 1 of the damping ratio, the displacement at the next peak in the positive direction will be. And they're asking us to write it in the form of integer. Let's try to first calculate zeta. Zeta value they have given us as zeta is equal to 1 upon 2 pi ln of 2. If you simplify it, it is 0.1103. So this value they have clearly given us. Another points to talk about it is we know that the logarithmic decrement, how it is related to the two consecutive displacement. So or two consecutive amplitude. So in this case, let's say x naught by x1 can be expressed as e to the power delta, where delta is nothing but a logarithmic decrement. Logarithmic decrement. So now let's say delta can be found by using, and you calculate this delta by using formula 2 pi zeta divided by under root of 1 minus zeta square. Okay, so in this case 2 pi zeta is 0.1103 divided by under root of 1 minus 0.1103 square. If you do, you will end up with a logarithmic decrement of 0.69728, and then you will use this value here, x naught by x1 is equal to e to the power 0.60728. They have given x naught value as 4 because you can clearly see in the question that a displacement peak in the positive displacement direction is measured to be 4 mm, and they are asking about the next peak. So x first peak is given to you, that is 4. Next peak is what they are asking, and that is equal to e to the power 0.69728. So x1 can be calculated as 4 divided by e to the power 0.69728. You will get it as approximately 2 mm. Okay, hence you have to type answer here as 2 mm. Okay, I hope it is clear. Okay, coming towards the next question. This is again from the mechanics. A rigid homogeneous uniform block of mass 1 kg. The height of this block is 0.4 meter. Width of this block is 0.3 meter. Is pinned at one corner here, you can see, and okay, and placed upright in a uniform gravitational field supported by a roller, as shown in this figure. A short duration impulsive force F is producing impulse of IF is applied at a height D, which is equal to 0.3 from the bottom as shown. Assuming all joints to be frictionless, the minimum value of IF required to topple the block is. Okay, so question here is, what is the minimum value of IF required to topple the block? Um, Let's try to understand the situation here. So first of all, um, what is happening here? Okay, IF is in impulse because of the force we are applying, and in this case, basically, um, if you apply that impulse, what is going to happen is, let me show you. Let me draw the figure here. Yeah, so something like this, the block will look like. Okay, and let's say, okay, not maybe not this. Mm, okay, imagine like, okay, let's keep it as it is. So this is the point, and now let's say this is the point, right? So imagine that initially, so basically, if you tilt that block, the point at which impulse is acting is now changing. So let's call this as a point G, maybe, and here it will become G dash. Okay, some weight is acting here. Um, okay, let's call it a G and G dash for the time being. You know that this G is um, at what distance? It is 0.3. Okay, 0.3 distance. Or yeah, not, I think, yeah, let's not take G. Let's talk about a G point. Let's take a CG here. CG is somewhere here, and now it will be somewhere here. Okay, let's talk like this, not the force F, so that it will be easy for calibration. So this is the center now, and this is G dash. The distance between G and G dash is, let's call it as H dash. Initial H is 0.4. H dash is a new terminology which we have introduced now. We know that G, this distance is 0.2, this height is 0.2, right? So here also this distance has to be 0.2. We don't know this distance. We know this angle, like this is 90 degree, of course, and if this is the center, CG is as the center here. Is it symmetric? This will be 1.5, this will be 1.5. So in this case also, this is 1.5, this is 1.5, and this height is 2. So we know that, let's call it as O here, this point as O. So OG dash can be written as, let me write on the next slide. OG dash can be written as, by Pythagoras theorem, 1.5 square plus 2 square. 1.5 square plus 2 square, right? So it will give me the, okay, I think not 1.5, 0.15. Let me correct it. 0.15, and height is 0.4, so it will be 0.2. Half of it will be 0.2. Okay, now it is perfect. So 0.2 whole square plus 0.15 whole square. You calculate it, you will end up with 0.25 meter. So now OG dash distance is 0.25. However, we know that the O to G distance, okay, or half of the height of the block, this block is 0.2 mm. So you can say that this H dash is now, H dash is equal to OG dash minus 0.2, and that will be 0.05. Okay, so this is height you are calculating. So this we know as 0.2. So H dash plus 0.2 is equal to the 0.25 which we have calculated. So H dash can be calculated as 0.25, which is OG dash minus 0.2. So we got this H dash. What is the use of it we are doing? We are making use of this height because it is because of this impulse. what is going to happen is there will be a change in the kinetic energy, sub initial kinetic energy, or let's say total energy in the beginning has to be same as the total energy after this impact, because the block is going to get some potential energy now because its CG is shifted by H dash, okay, or increased by H dash, so it will have some potential energy associated with it. So I'll say by energy balance, kinetic energy plus potential energy in the initial time or in the beginning is equal to kinetic energy plus potential energy the final time. Okay, there is no potential energy in the beginning. Kinetic energy, we can say half of I about 0.0 omega square. Okay, I omega square. Now uh, is equal to, let's say in the second case, there is no kinetic energy, but we do have the potential energy because of that H dash. So mgd H dash we have. So yeah, these are the two things. Now the I can calculate as in this case 1 by 3 times h square plus b square. It will be 1 by 3 times height is 0.4 square plus 0.3 square, and you will end up with 1 by 12. Okay, so that is our I. So half of 1 by 12 into omega square is equal to mass is 1 kg, acceleration due to gravity is 9.81, and h dash is we just calculated 0.05. If you simplify this for omega, you can say that omega will be equal to 3.43 radian per second. So we got the value of omega in this case. Okay, the value at which you are basically turning or rotating this box or block about that pinned point O. We know that according to the impulse momentum principle, what they are asking us, they are asking us to find the impulse. Okay, we are supposed to find the impulse. According to the impulse momentum principle, we know that angular impulse is equal to change in the moment. Angular impulse is equal to the change in momentum, right? This is the impulse momentum theorem. So if into d, okay, at what depth we are applying it, so that is 0.3 in this case, is equal to I naught omega initial minus omega final. So if into 0.3 is equal to 1 by 12. I naught we just calculated already. Omega I is 3.43 we just calculated, minus omega final is 0. So now from this you can say IF is equal to 0.953. This is the answer. So in this case they are not given us the option, so you have to type it as 0.953. Oh, I think yeah, they have given the options. Option A is correct in this case. Sorry for this. Okay, so correct option in this case is option A. So what we have done, we have first of all used the energy balance equation to find out the omega, and then we have applied the impulse momentum principle to calculate the impulse. Next question. This is from the balancing chapter. A rigid body in XY plane is consist of 2-point masses, 1 kg each, attached to the end of a massless rod. Okay, these are two massless rod, each of 1 centimeter in length as shown in this figure. It rotates at 30 rpm counterclockwise direction about Z axis passing through point O. The point mass of root 2 kg is attached at one end of third massless rod. So basically, there is one more massless rod. We don't know what is the length, but here we are attaching it whose mass is root 2 kg. Okay, I'm repeating the question. A point mass of root 2 kg is attached at one end of the third massless rod and is used for balancing the body by attaching the free end of the rod to point O. Okay, the length of the third rod in centimeter is. So what is this length? They're asking. We know that the basically mr omega square, omega is common in all these cases, so mr square basically mr bracket square, or let's say the resultant of these two has to be same as the resultant of the, or the, let's say, the counter mass. Okay, so we have two masses of 1 kg. Those will create a centrifugal force when we rotate it at certain omega, and the counter mass which you are using of mass root 2 at a certain radius r, that has to be balancing, the, let's say, the centrifugal force created because of it should balance the centrifugal force created by the two masses of 1 kg. So we can say that m1 r1 whole square plus m2 r2 whole square, because I'm not considering omega in this case, because of course it is same in the for the counterbalance mass as well. So this has to be, under root of this has to be equal to balancing mass and the radius of balancing mass. R is 1, m is also 1, so it is 1 square plus 1 square, that is equal to mass is root 2, rb is we don't know. Okay, under root 2 is equal to under root 2 into rb. This implies rb has to be equal to 1. Okay, hence the correct option is option A in this case. Okay, since they have given us that counter, the balancing mass is root 2, can see that on the left hand side we are getting root 2, and on the right hand side it is root 2 rb, hence rb has to be 1. Coming towards the next question. A spring mass damper system in which we have mass m, stiffness k, a damping coefficient c, excited by a force f of t is equal to b sine of omega t, where b, omega, and t are the amplitude, frequency, and the time respectively, shown in the figure. Okay, so here we are talking about the amplitude versus time, how it is varying. They have given some options. Okay, now in the figures, the response of A is the amplitude of the response shown in the red color, and the dashed line indicates the envelope. Okay, here these are the dashed lines which shows the envelope. The response represents only the qualitative trend, and those are not drawn to a specific scale that they have clearly explained. Further, the question says that four different parameters and forcing conditions are mentioned below. First condition is C is greater than 0, omega is equal to root k by m. C is less than 0, omega is non-zero. C is equal to 0, omega is equal to root k by m. C is equal to 0, omega is approximately equal to root k by m. Whenever they say C is 0 means we are not using damping. Okay, C0 means no damping. So the last two cases, R and S cases, are with no damping. Whenever they say omega is equal to root k by m, it means the exciting frequency is equal to the natural frequency. Okay, so omega, omega n is equal to root k by m, and if omega is equal to omega n, that is the case of a resonance. Question here is, which of the following options gives you the correct match of the parameter with the forcing condition to the response? So basically you have to match this PQRS with 1, 2, 3, 4, which, so you have to match PQRS with 1, 2, 3, 4. Okay. So let's try to understand each and every situation here. The easier situation, let's say maybe will be S, let's say, starting with S. C is equal, S and R basically. Here we don't have damping. So let's say in this case, you don't have damping, and also your frequency is not exactly equal to the, you can say, the natural frequency. So the response will be the way it is here. Okay. So like, I would say that because the forcing is sine of omega t, so the response will be in the similar way you will have with the no damping. So amplitude will follow this trend. So for the S, you can say the option 3 is the correct one. Okay, at this stage itself, you can conclude the answer that option C is correct. But yeah, we will understand each and every case in this. About the second case, C is equal to 0 and omega is equal to root k by m. In this case, we are not using the damper. We are not using damping. So, and omega is equal to the natural frequency. So vibrations will increase. Okay, vibrations will increase. They will not decrease. So that's why option 3 is gone here, because here vibrations are decreasing. So this is gone. In this case, the option 2 is correct, because in this case, we'll have a linear change in the vibration. Okay, so the vibration will increase like this. So option 2 is correct in this case. So R2 is correct. Why? Because the this trend you will follow in whenever you have an under damped situation. Sorry, whenever you have a over damped situation. Okay, so let me show you mm, what I mean. So let's talk about the Q situation here now. Q situation is C is less than 0. Okay. Mm, C is less than 0 indicates what? C is less than 0 means zeta is also less than 0, right? So you can say it as an under damped situation. Okay. So of course you are doing under damping means vibrations will increase in this case, and it will lead to the this figure that it will increase in the parabolic way. So I would say for Q, the fourth figure will represent. Okay, so this is the case. You can say C is less than 0. Okay, because in this case zeta is less than 1. In this case, I would say it is C is equal to 0 and omega is equal to root k by m. In this case, I would say it is C is equal to 0 and omega is not exactly equal to, but approximately under root k by m. And yeah, remaining case is the P. C is greater than 0 means it is a case of zeta is greater than 1, that is over damped situation. So damping will after some time will decrease over time, and that's why this kind of behavior it will have. Here they have given omega is equal to root k by m. So after some time it may decrease. Hence, for P it is 1, Q it is 4, R it is 2, and S it is 3. Option C is correct in this case. Coming towards next question. This question is from trusses. The length of member BC and CE in frame shown in the figure are equal. So where is BC? BC is here and C is here. All the members are rigid and lightweight, and the friction at the joints is negligible. Two forces of magnitude Q greater than 0 are applied as shown in this figure. Each at the time, each at the mid length of the respective members on which it acts. Which one or more of the following members do not carry any load? So they are asking us to check like which one or more members do not carry load. So basically, let's see how to find it. If you look at the point G here, okay, let's try to draw the point G here. So the options is A, B. Let's talk about all. A, B is there. At point A, we have the we can clearly see there is a support, and yeah, if there is a reaction at point A, of course there will be some force in the member AB. Next option is CD they have given. In this case also same, we are applying Q here. So if there is a force in CD and there will be force in EF, because at point D and E, it's like pushing, right? We are pushing here, so there will be some reaction. If you are pushing here, there will be some reaction at point D and F. So I will say we cannot say that these two options are correct. But what about GH? The GH, if you try to draw the free body diagram of the joint G, let's say this is your joint G, and this is H, this is E, and here it is B. Okay. What we can say here, we can say that this is the condition where at a joint, 3 members are meeting out. However, 2 members are collinear, means whatever force you can say in this direction, use the laser pointer here. In this direction, whatever force is there, that will be balanced by the force in this direction, right? I hope you are following. We are talking about this joint. So whenever we have a 3-member meeting out at a certain joint and 2 members are collinear, then the force in the third member is 0, provided that there is no load or the reaction at that particular joint. Okay, at this particular joint you don't have any load or any reaction, and that's why you can say that in this member GH there will be no load, because these two are collinear. Hence the option D is correct in this case. Okay, if you want to write the statement, please write it. If at a joint 3 members are meeting and out of those 3, 2 are collinear, then the force in the third member will be 0, provided that there is no load or reaction at that point. Okay, because you can clearly see here the force in the GE and the GB will be balanced, and there is no role of GH in this case. Okay, unless and until you are not applying an external load on at point G. Coming towards the next question. Yeah, I think this is the last question from this paper. In the configuration of a planar 4-bar mechanism, at a certain instant shown in the figure, the angular velocity of 2 centimeter long link omega 2 is 5 radian per second, given the dimensions as shown. So they are given dimensions of this link as let's call this link as link number 1, this link as link number 2, this link as link number 3, or maybe let's call this as a 1, sorry. Fixed link is 1, 2, this will become 3, and this will become 4. Okay, this is the nomenclature for the link. Now, what they have given is, given the dimensions as shown, the magnitude of angular velocity omega 4 of the 4 centimeter long link is given by. Okay, so at this stage, this omega 4 is what they are asking. You can solve this by either drawing a velocity diagram or instantaneous center method. Okay, to save that some time, we can use the instantaneous center method. You can clearly see whenever we have two links together joining at a point, that point will be an instantaneous center. So I12 is a fixed eye center, 2 to 3 is a permanent eye center, then again 3 to 4 is again a permanent eye center, and then this is again link 4. This is 4 and 1, so I will say I14 is again a fixed eye center. So these are easily found eye centers. So what are the rest of the two eye centers now? Eye center 1, 3 and eye center 2, 3, right? How you calculate the eye center 1, 3? Eye center 1, 3 and eye center 2, 3. Eye center 1, 3 is found by joining two lines. One is I12, I23 and I14, I34. Let's talk about it. I12, I23. Where is I12? I23. So if you extend this horizontal line, on this line there will be somewhere an eye center 1, 3 will be there. Okay, that is what we are saying. Okay, what is the another line? Another line is I14, I34. I14 is somewhere here, I34 is somewhere here. So basically the line, horizontal line and this line. Let me use maybe this yellow pen here. This is the first line which is passing through I12 and I23. And the second line which is passing through I34 and 14. These two lines are meeting at the same joint as I14. So we can say that I13 is also at the same place at this particular instant. In the same way, you can find the eye center 2, 3. Eye center 2, 3 can be found as joining the eye centers. Sorry, it's a 2, 4, not 2, 3. Eye center 2, 3 and eye center 2, 4. Eye center 2, 1. Eye center 1, 4. Okay. 2, 3 and 3, 4. Okay, let me correct. Eye center 2, 3 and 3, 4. Where is eye center 2, 3 and 3, 4? Eye center 2, 3 is here. 3, 4 is here. So you have to draw a line. I'll use maybe, yeah, this yellow pen. One line will be passing through these 2 points, and another will be 2, 1 and 1, 4. 2, 1 and 1, 4 is this horizontal line again. Okay, so these two are meeting at a I23 itself. So of course, the new eye center now I can say that I24 is also lying here. So this is a special situation now because of this figure, or let's say the way the mechanism is shown in this figure. I center 2, 3 and I center 2, 4 lying on the same point. I center 1, 4 and I center 1, 3 is also located at the same point. Okay, so now we have found out all the eye centers, and by using eye center method, we can calculate the required velocities. So, okay, required angular velocities omega. Let's start the calculation part here. Okay, so what we can say that let's say I want to calculate the velocity of, let's say, this particular point here. How can I calculate? Omega 2 into, if I consider it a part of link 2, omega 2 into I12 to I14 distance. I12 to I14 distance, right? I'll get the velocity of that point. However, if you consider it as a part of fourth link, okay, because I center 2, 4 also lies there. So if you can consider it as a part of fourth link, it can be written as omega 4 into I24 to I14. Okay, so you can consider this as entire link here, which is rotating at omega 4, and using this also you can calculate the velocity at that particular point. So velocity will be omega 4 into that distance I24 to I14, and yeah, with that I can say that omega 2 is given as 5 into I12 to I14 distance is 2, omega 4 I wanted to calculate, and I24 to I14 distance is 10 minus 2, which is 8. Okay, this particular distance is 8. So we can say that omega 4 is equal to 10 by 8, 1.25 radian per second. So 1.25 is the final answer in this case. Okay. We have to round off the answer up to 2 decimal places. Yeah, so yeah, that is the correct one. So that's all from this paper. Thank you all for watching this video.